Hi, everybody. As promised, I'm going to make a video version of the extra spectroscopy practice that we did in class. Just so you know, I rearranged things just to put all the multiple choice questions first, and I'm going to go through it quickly so this video doesn't take too long. Because, in class, we went over it in detail. Okay, so first things first, you got to know what each spectrum does and how it does it. All right, so the first question here says, what is a disadvantage using infrared spectroscopy? So remember, infrared only tells us which bonds are present in the molecules. It does not tell us how they are arranged, making D the correct answer. Number 2 is about the mass spec. Which statements are correct about the molecular ion in the mass spectrum? So remember, when a sample goes into the mass spectrometer, it's blasted with X-rays. Now, it does say during electron bombardment, so maybe I'm wrong about that. But anyways, it's blasted with ionizing radiation, which causes electrons to be knocked off from the structure of the molecules. Sometimes, then the electrons are knocked off from the electrons in the chemical bonds. So some, but not all of the molecules are fragmented when they go through the machine, broken into bits. The molecular ion represents the mass to charge ratio of the entire compound. So let's look at 1, 2, and 3. The molecular ion is not always the peak with the highest intensity. Well, that's true. If the bonds between atoms are relatively weak, then a lot of the molecules will be broken apart. Right? So in class, we looked at the mass spec of carbon dioxide. In that case, the molecular ion was the highest because those carbon-oxygen double bonds that are present in carbon dioxide are very strong. All right, so the molecular ion is always the most stable. Well, no, because if it were the most stable, it would have the highest intensity. And the mass to charge ratio of the molecular ion peak gives the relative molecular mass. Yes, that's true. So the answer is B, 1 and 3 only. All right, number 3 says, which compound gives this NMR? So easy peasy lemon squeezy, we're only given a non-high res NMR. I see 3 peaks. Something tells me among these molecules, only one of them will have 3 hydrogen environments to produce those 3 signals. So if we look at choice A, there is no symmetry here. So I got 1, 2, 3 environments. I'm tentatively going to say that it's A, but let's look at the others just to be sure. All right, so in this molecule here, we have, this is an ether, by the way. We have, direct symmetry. A line of vertical symmetry down the middle, which makes 1, 2 environments. So it can't be C. And the alcohol here, again, there's no symmetry. So we have 1, 2, 3, 4, 5 environments. So it can't be that. And in this alcohol, this is a tertiary alcohol. Yeah. We have 1 and 2 environments because all those methyl groups are equivalent. So it is indeed A. All right, number 4, which region of the electromagnetic spectrum is used for NMR? Again, you just got to know it, radio waves. All right, so what information do we only get from the splitting pattern? So remember, the NMR gives us 3 bits of information. The number of chemical environments of hydrogen. It gives us the integration trace, which is the ratio of hydrogens in each environment. But for smaller molecules, it tends to be the actual number of hydrogens, and the splitting pattern, which tells us the number of hydrogen atoms that are on adjacent atoms, making B the correct answer. All right, so number 6 is, what are the number of signals and the splitting of these signals in the NMR of propanone? So strong recommendation, take the time to draw out your molecules. So this here is propanone. Now again, we have a nice line of vertical symmetry there. That means each of these methyl groups is in the same environment, which means we'll have 1 signal in the NMR. And because on the neighboring carbon atoms of the environment, there are 0 hydrogens, it will be a singlet. All right, for number 7, it says, which compound has this high res NMR? So again, I think there's 2 peaks. That's either splitting or it's 2 peaks that are squished together. All right, so if it was propane, let's just draw them all out because that'll help us. So propane would have 2 environments, so 2 peaks. So it could be that. 1 environment, 2 environments. Propanal would have 3, CH3, CH2, CHO. Propanone would have 1, and propanoic acid would also have 3, so it must be propane. All right, so number 8 says which compound produces the following high-res NMR? So not only are there 3 peaks here, the 3 peaks would tell you that there's going to be 3 environments. We already know in propanone there's 1. In propane, we know there's 2, so it can't be that. In methylpropane, I'm being quick here, right? Ooh, all 3 of those are equivalent, so there'd be 2, so it's propanal. Another thing to think about, you see that peak all the way out there between 9.5 and 10? You should recognize that as being the hydrogen bonded to the carbonyl in an aldehyde. So 2 ways to know that that is for propanal. Now, moving right along, done with the multiple choice. All right, so 2-methylpropanoic acid and its esters are found in foods. Great. Predict the number of signals and the ratio of areas under the signals in the NMR of this compound. All right, so the area under is the integration trace. The number of signals is the number of environments. There's no symmetry here whatsoever. So 1, 2, 3 environments, so 3 signals. And for the integration trace, the area under the signals, in this case, will just be the number of hydrogens. So 3 plus 3 is 6 in one environment, 1 in the other environment, and 1 in the final one. Does not matter which order you put the ratio. It could be 1 to 6 to 1, or 1 to 1 to 6, or whatever. All right, so predict the splitting pattern of the signal of the hydrogen atoms on the circled atom. All right, so again, the splitting pattern tells you how many hydrogen atoms are on the neighboring atom to that environment. So there's 1 on that environment, so that would be a doublet. Right. Identify the fragments with the mass to charge ratio of 73 and 43 in the mass spec. Use section 22. Where did I put my data booklet stuff? All right, so when I look, I'm going to look for a mass of 73. Drat, it's not there. Neither is the mass of 43. So when this happens, what you need to do is work out the molar mass of the compound. There are 1, 2, 3, 4 carbons, 6, 7, 8 hydrogens, and 2 O's. When you add that all together, you get a mass of 88. So what this means is the molecule with a mass of 88 broke into 2 bits. One thing that broke off was 73. So 88 minus 73 is 15. 15 is for a methyl group breaking off. Now, it's for a methyl group breaking off, taking one of the bonding electrons to make a methyl radical. So that means we're going to have a radical species produced because one of those bonding electrons was left behind. So the methyl group is CH3. Just subtract a C and 3 H's from that bad boy. So it's going to be C3, H7, O2, and the dot for the radical. I was asked about that in class. I thought about it a little bit. Some of the fragments are not radicals, others are. If a radical is formed, it leaves a radical behind. All right, so mass to charge of 43, well, 88 minus 43 is 45. And the mass to charge of 45 is a carboxyl radical. So this has 1 carbon, 2 oxygens, and a hydrogen. Same thing, just subtract it from that. So we're going to have C3, H7, and don't forget to make it a radical. All right, so predict the wave number of one absorbance other than the carbon hydrogen in the infrared spectrum. All right, so a couple you could do. We would see an absorption for the OH. We would see an absorption for the C double bond O and one for the C single bond O. So if asked for the wave number, the C double bond O will be between 1700 and 1750. If it says to predict, give a number in that range. So anywhere between 1700 and 1750 will do. If it's the OH, remember this is a carboxylic acid, so it'll be a value between 2500 and 3000. And finally, for the carbon oxygen single, it'll be between 1050 and 1410. So if you're asked to predict, that means pick a value somewhere in there. Okay, aspirin was synthesized by mixing salicylic acid with excess ethanoic. So I kind of like broke these problems all apart, so we don't need all of them. So it says deduce one absorption in the infrared of both aspirin and ethanoic anhydride, and one that only appears in aspirin use section 20. All right, so what we got to do, the infrared tells us the bonds. So let's work out the polar bonds. We got C double bond O, we got C single bond O, we got C to H. So C to H would be in both spectrums, C double bond O or C single bond O. Any of those would work there. Now, when I look at aspirin, there's one thing in aspirin that we don't have in ethanoic anhydride, and that is a carboxyl group and the OH on the carboxyl group. So we would see an absorption for the OH, and that's for the carboxylic acid, so that would show up somewhere between 2,500 and 3,000 wave numbers. Structures of compounds can be determined. Yeah, that's what we're talking about here. So ibuprofen has some impurities. Here's ibuprofen. Here's an impurity that they're calling X. This is going to continue on the next page, so we'll kind of do this. It says predict the number of signals and the relative areas you would see in the NMR of the circled side chain. So the number of signals is the number of environments. 1, 2, 3 in ibuprofen, and no symmetry, so 1, 2, 3 in impurity X. The relative areas in this case will just be the number of hydrogens in each environment. So 3 to 1 to 1, 3 to 1 to 1, and the other one will be 2 to 2 to 1. All right, moving right along, we have now impurity Y. And it wants to know 2 reasons which spectrum belongs to impurity Y. All right, so let's look. First things first, I see the OH in an alcohol. So if we look at the infrared, that OH bond is going to be strong and broad, more like a spoon than a knife, and it's going to show up between 3,200 and 3,600. Ooh, there we go. I already know it's spectrum B because of the presence of that OH absorption. Now, the rest of this molecule, there's nothing in here that's really all that distinct. Right, so we got carbon to hydrogen. Really, it's just carbon to carbon and carbon to hydrogen. So what I did was instead look at a peak in spectrum A, or an absorption, excuse me, that appears in spectrum A that would not be here. So this absorption right here around 1700 is for a C double bond O. We have none of that in our molecule. So I said the presence of the OH and the absence of the C double bond O are my 2 pieces of my 2 reasons. All right, math time. All right, so number 12 says an organic compound A has the following composition by mass when its only combustion products are carbon dioxide and water, and they are analyzed. Outline why it's not a hydrocarbon, because it probably contains oxygen, so it contains another element other than C and H. Not bonded, but C and H. Sorry, that looks terrible. C and H. All right, determine the empirical formula. So we're given percentage by mass. All right, so 71.93% carbon. Well, if that were, if we had 100 grams of the compound, then that would be 71.93 grams. We have 12.10 grams of hydrogen, and we have, we got to figure out how much oxygen we have. So we have 71.93 grams of carbon, 12.1 grams of hydrogen. We subtract that from 100, if I can use my calculator, we get 15.97 grams of O. So that's grams of C, grams of H, and grams of O. All right, to get the empirical formula is just the ratio of moles of carbon, hydrogen, and oxygen. So to go from mass to moles, we divide by the molar mass. So I'm going to do that for each of these. When we divide 71.93, slow down, dude. By 12.01, we get 5.99. That rounds nicely to 6. So 6 moles of carbon. 12.01 or 12.10. I'm so used to the molar mass of carbon. divided by 1.01 is 11.99. That pretty much rounds to 12 moles of H, and 15.97 divided by 16 is 0.998, which rounds to 10. So C6H12O. And a sample of vapor A at 200.0 Celsius and 10,000 or 1.00 times 10 to the 5th kPa's has a density of 2.544 times 10 to the 3rd grams per cubic meter. Determine the molar mass. All right, so we're given a pressure. We're given a density, which means we're given a volume is equal. R is a constant. We're given the temperature. So we can calculate the number of moles using PV equals nRT. Now remember, this N factor is the number of moles, which is equal to mass divided by molar mass. So let's redo this equation. PV equals mass over molar mass times R times T. So we're asked for the molar mass here. So all we got to do is some algebra and rearrange. So the molar mass will be equal to the mass times the gas constant times the temperature in Kelvin, divided by the pressure times the volume. A little algebra action. So the mass, this is 2.544 times 10 to the 3rd grams per every 1 cubic meter. So the mass is just 2.544 times 10 to the 3rd times R, which is 8.31, times T. Well, we got 200 Kelvin. So we have, I'm running out of space, 473, or we got 200 Celsius, excuse me. So 473 Kelvin divided by the pressure, which is 1.00 times 10 to the 5th, times the volume, which is 1. And when you plug in, you get an even 100. But for sig figs, we got 2 there, 4 there, 4 there. So I rounded 2 to represent 100 with 2 sig figs. You do 1.00 times 10 to the 2nd. And that is the molar mass. We need the molecular formula. Well, 6 times 12 plus 12 plus 16 equals 100. So the empirical and the molecular formula are both the same. All right, the infrared spectrum of A is shown below. Identify the bond responsible for the absorption of B, labeled B. You don't know what I did with that page of the data booklet, but if you look, you'll see this is about at 3,300 or so. It's broad, so that is for the OH in an alcohol. A can be converted to compound E, which has a higher molecular mass, by heating it under reflux with acidified potassium dichromate. So this is the oxidation of this alcohol. Now, when you oxidize an alcohol under reflux, first you produce an aldehyde. Now, the only difference between the alcohol and the aldehyde is the loss of one hydrogen. So the aldehyde would actually have a lower molecular mass. But the second product that's formed would be a carboxylic acid, which is oxidized via the gain of oxygen. So the carboxylic acid will have a greater mass. So it's got to be a carboxyl group. You can either write carboxyl group or COOH. Deduce a possible structure. So we already know this is C6H12O. We know it's a primary alcohol because it produced the carboxylic acid. Also, if it was secondary, it would produce a ketone, again, which is just produced via the loss of hydrogen. So the ketone would have a lower molecular mass. That's how you work out its primary. So let's put 6 carbons in a chain. 1, 2, 3, 4, 5, 6. We'll put the OH at the end. There's 12 total H's, so let's go ahead and distribute them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I kind of did this randomly, but it doesn't matter. These two need a bond, so there must be a double bond. I actually looked at the mark scheme. It's any primary alcohol with 1 double bond between carbon atoms. Yeah, 1, 2. I wonder if you could do this. I wonder if you could just make it phenol. But anyway, I'll see one. All right, so identify one absorption in the range of the infrared spectrum of ethanoic acid that's not in the alcohol. Okay, so I don't have, you're just gonna have to take my word for it. So there is a OH bond absorption between 2,500 and 3,000 wave numbers that's going to show up in the acid. There will be an absorption for the OH bond in the alcohol, but it's between 3,000 and 200s. I would always just give all the information you can, because I don't know if they're looking for the range, a specific one, or the bond. So you can just give it all. So you can say approximately 2,700 wave numbers. All right, last question. And we're only at 20 minutes. Let's go. Predict giving a reason. Deduce giving a reason whether the following NMR is of ethanol or ethanoic acid. Okay, so ethanoic acid has 2 hydrogen environments, which means it's got to be ethanol. But the number of hydrogen environments won't answer this. We're told to use section 21. So we know it's an alcohol. So there it is. The H from the alcohol will show up between 1 and 6. If we had a carboxylic acid, we would have a peak in the NMR somewhere between 9 and 13. So when we look at this, it's the alcohol, not for the number of hydrogen environments, but the absence of the peak in that range. And finally, predict giving a reason the splitting pattern of the signal produced by the hydrogen atoms in the methyl group in ethanal. Ethanal is the aldehyde. So the splitting pattern for the methyl hydrogens, the neighboring carbon has 0 hydrogens, so that would be a singlet. It's not as hard as you think it is. Thanks for watching, and I will see everybody in class on Monday.